moving into a geometry chapter. Um, good. So when I tell you geometry proof, are you still excited? So we're going to start about talking. We're going to whatever. We're going to start talking about parallel lines and the importance of using appropriate definitions. So on your paper, you see 1 through 5 and a set of parallel lines. Somebody give me the definition of parallel lines. Never intersect. Okay. What's another one? How else would you define two lines that are parallel? Same slope? Okay. All right. If you look at those parallel lines, let's pretend you know nothing about math. Some of you, that's harder to do than others. If you didn't know any math terms, how would you describe those two lines? If you didn't know parallel, you didn't know slope or any of those terms. Next to each other? Okay. Okay. How else? Okay, so you're describing the lines themselves as straight. Okay, how would you describe their relationship to each other? And we have that, never intersect. We got to come up with at least two other ways. Identical how? Okay, if you didn't know the word slope, what would you say? Well, you could maybe... Okay, let's use same direction. Okay, can you think of another way to describe the relationship of one line to the other line? Kind of a big one we're missing, nobody's said yet. Somebody came up with something today I never thought of, so I'm leaving this up to you guys. Would you describe the relationship of one line to the other? Well, no, and you missed the part where I said you're not allowed to use parallel or slope or any of the math terms. So if you were new to geometry, how would you describe those two lines? Not the lines themselves, but the relationship between the two lines. Meaning, so am I hearing this? Now this is a math term. So maybe I won't use the math term and I'll just say this. Meaning that the distance between the two lines remains constant. Not the lengths of the lines, but the distance between the lines is constant. Okay, so here are 5 ways to describe parallel. We're going to compare these 5 ideas against actual sets of lines and see, are they in fact parallel? So, look at letter A. According to definition 1, are those two lines parallel? Yes. So that would be a yes. According to number 2, are they parallel? No. So I cross those off. According to number 3, are they next to each other? Well, what did you mean by next to each other? I don't remember who said that. So would you consider those next to each other? You're the definition master. And I don't care if you say yes or no. A. No. Okay, he said no. So, do they travel in the same direction? No. Are they equal distance? No. Are those lines in fact parallel? No. So, we automatically have a problem. Our definition number 1 has an issue. Okay? So, that's what we're going to do on all of these. So, letter B. Number 1. Yes. 2. No. 3. Jackson, you get to pick. You came up with the definition. No. Okay. 4. No. 5. No. Okay. Are they parallel? No. All right. C. 1. Yes. 2. Well, it kind of depends. Do they have the same actual steepness? Yes. Do they have the same XY slope? No. So it depends on what you mean. This would be considered a negative slope, and this would be considered a positive slope. So if you're talking about XY slope, the answer would be no. But if all you're doing is talking about steepness, then the answer is yes. So it depends on what you meant by slope. Let's go ahead and say yes, they have the same steepness. 3, no? How come? Okay, so he's saying no because they're traveling away from each other. 4, kind of. Would you explain yourself, Derek? Right, if you're going up, the answer would be no, but if you're going down, the answer would be yes. So that's kind of half yes, half no. Are they equidistant? Certainly not. All right. Oh, were they parallel? No. Letter D. 1. Yes. 2, yes. 3, yes. 4, yes. 5, yes. Are they parallel? Yes. So that's good. All of our definitions worked when the lines are actually parallel. So that's half of what a definition needs to do. It needs to include the actual things that you're trying to define. So we're halfway there. Now, looking at E, I actually want to change E. Let's change it to look like this. Okay? And we'll talk about this version of E in the original. So, number 1. Yes. Number 2. Yes. At every horizontal point, the slopes are in fact the same. Number 3. Jackson? Yeah, certainly. Number 4. Yes. Number 5. Yes. Are they parallel? No. Why not? They're not, in fact, lines. They're parallel squiggles, but they're not parallel lines. Okay, so let's look at E, the actual E. They don't intersect. Do they have the same slope? It depends. They have the same sort of steepness, but if you're talking about X and Y slope, then no. Are they next to each other, Jackson? Yes. Same direction? At the endpoints, right? So here and here, the directions are opposite, but at the endpoints, yes. Are they equal distance? No. They're equal distance here, here, and here, but in between, the answer would be no. Okay? And last one. It's kind of hard to see. Never intersect. Yes. Same slope. Yes. Next to each other. I would say yes. Same direction. Yes. Equal distance. Yes. Are they parallel? No. They're not. Why are they not parallel? They're not parallel for the same reason that E is not parallel. They're not, in fact, straight lines. And not for the reason you guys think. So, did we have a definition that passed the test? Did any definition have yeses when it was supposed to and nos when it wasn't? No, they all failed. Why did they fail? For instance, why did number 1 fail? Okay, so letter A, number 1 failed in letter A because those are segments, not lines. So when we talk about parallel, is it possible for two segments to be parallel? Yes, a square has two sets of parallel segments. But we want to make the definition parallel lines. Okay? So we need to include that. We're going to create a new definition. We want to use the word line. Okay? Why did number 2 fail? Does everybody understand that? So let's say we both went skiing or snowboarding. Okay? We started in a valley. We both, maybe I should draw a picture. Make more sense. So we start here, I walk up and I ski down this slope, and you walk up and you ski down that slope. If those two slopes have the same steepness, does that mean that the two slopes are parallel? No, because you can obviously see they're going to intersect. So when we talk about slopes, especially three-dimensional slopes, the steepness needs to be on the same plane. Okay? If you have a three-dimensional space, slope is a two-dimensional idea. It's the y value divided, the change in y divided by the change in x. That's a two-dimensional idea. So in order for slope to be a factor, they have to be on the same plane. And this same plane idea is actually the other three. Well, no, 5. What's wrong with 5? Why did 5 fail? Which one did it fail on? E? Why did it fail? Because they weren't lines. So if we said lines that are equidistant, would that work for parallel? Yes, that guarantees they're in the same plane. So that's one definition you could use. You could say two lines that are equidistant. All right, so for our new definition, let's say two lines, this is the bottom of the page, that never intersect two lines, whatever, that also lie in the same plane. Now that's not the only way to define it. You could say two lines in the same plane that have the same slope. You could say two lines that are equidistant. And when we say lines, we mean straight lines. All right, I want to talk a little bit about F, but I'm going to talk about it in a strange way. Back 2,000 plus years ago, there was a guy in Greece named Euclid. He is considered the father of modern geometry. He is the reason you guys do proofs, so you probably don't like him. But because of him, we know a lot more about mathematics than we would otherwise. So what Euclid decided to do was take the Pythagorean theorem, which is a squared plus b squared equals c squared. And we knew that it worked. We'd known for a long time that it worked. In fact, before Pythagoras, we knew it. But he got the credit somehow. So what Euclid wanted to do was prove that that was true. Always, for all triangles, which to you seems silly, but in mathematics it's really important. So he wrote a book called Euclid's Book of Elements, and book 1, I think there are like 12 or 13 books, I don't know. But in book 1, he wrote 47 proofs. And each proof built on itself. So, he proved something really simple and then kept building and building and building, and eventually he reached that. And he understood a lot better than you do, or I would have, that you only want to prove things, you want to use the minimal amount of information to prove something. Because as soon as you start throwing extra information in, you cut out mathematics. For instance, imagine there was a filter on the school, and we said, okay, everybody with brown hair can come in the school. Right? If we accept that as a necessary requirement to go to school, a lot of people are going to show up and then not make it through the door. And then if you said brown hair and blue eyes, then a bunch of other people are going to get thrown out. If you said blonde hair, brown eyes, and short, it's going to be me and a few other people. Right? What kind of fun is that? So these filters are called axioms. And I don't want to get too deep into this, but every time you accept something as true, you limit what you can do after that point. It's like putting a filter on, and you can change the filter to be whatever you want. If you want to decide that 2 plus 3 is 8, go ahead and do it. But the number system that we've developed no longer applies. So the number system as we know it would stay out, and your pretend math would work. And we actually do that all the time in math. You guys just don't realize it. So he made it to proof number 28, I think, somewhere in there in the 20s. And he introduced something called the fifth postulate. Postulates are mathematical ideas that you accept to be true because you can't prove them. For instance, one of his postulates was, if you have 2 points, there's only one line that goes through those 2 points. And he said, I agree, that's true. Okay? Well, that's his definition of straight. So what he has done is gotten rid of all of these other lines. So in Euclid's world, curved lines don't exist. By accepting that axiom, he threw out all these other lines. Does that make sense? Which was good, because if lines are squiggled, we run into other problems, but whatever. So on proof number 28, he introduced the fifth postulate, which said this. If I have a line and a point, this is going to really make you wonder what's going on. If I draw a line through that point such that this line is parallel to that line, I'm going to accept that this is the only solution. There is only one line that does this. Does that seem important to you guys? So basically he was saying that there is a unique parallel line through any point. Wow. Totally had a mathematical upheaval there, right? Well, he tried really, really hard not to do that. And in the end, he decided, I don't have a choice. I have to use it. And he ended up using it, even though he didn't want to, and then he proved the Pythagorean theorem. And lots of people after him tried to make the same proof, avoiding this fact. And it turns out that they just use other facts that are essentially the same as this. So is he right? Is there only one parallel line to any given line through a specific point? Okay. Stay tuned. Here's the Earth. Okay? Becca lives on the Earth somewhere else. And this is a perfectly flat Earth. It's not very big. And there are no oceans. It's probably colored pink. And it has dance music. So she's standing there. And she gets kicked out of her house. And she says, Dad, where do I go? And he says, I don't care. Just start walking. So she walks in a straight line. Okay? She gets around, walks around the backside. And despite what her dad said, she ends up right where she started. Everybody agree? That is a straight line on a sphere. I think, are you testing people done? You might want to, I'm only going to give you today, so you better hurry and finish. 22 minutes. So, on the Earth, a straight line is the path traveled if you start at any point and go in one direction until you reach back where you started. That is a straight line. On a straight line, you have two hemispheres of equal size. So on this basketball, this line is straight. Okay? So when Becca gets back to her house, her dad's mad at her and said, okay, I want you to walk, but this time I want you to take a big step with your right foot and a little step with your left foot. That way when you circle back around, you're not going to reach me again. So this is what she's going to do. Big step, half step. Big step, half step. And that's going to cause her to go in a circle. So if you did that, you would create that. That is not a straight line. Okay? Now, all of these are circles, right? Well, the first one is called a great circle because it's a circle that cuts the sphere in half. The other one you could term a lesser circle, I guess. I don't really know what we call them. A lesser circle has two uneven halves. Okay? And the only one that's actually straight is the great circle. So you guys have seen a map where you're flying from the United States to England and you want to fly that way and people tell you no, it's faster to go like that. Well, if you look on a globe, if I were to travel from here to here, well, it's hard to do, but from here to here, I'm going to go over the top. That's the fastest way. But on a flat map, it's kind of messed up. So great circles usually go over the top of the Earth, or kind of the top. So this actually has implications that you don't realize. That's the United States, right? The top of the United States is like the 47th or the 49th parallel. I don't remember. That part of the United States is not straight. It's curved. If you were to build a fence and you were to stand over here, that fence would curve. Okay? Utah, the top of Utah is not straight. The top of Wyoming, the bottom of Wyoming are not straight. It does have 4 right angles, but the bottom of Wyoming is actually 40 miles longer than the top of Wyoming. So that's pretty crazy, right? The left and right sides of Wyoming are in fact straight because the longitudinal lines on the Earth are great circles. The latitude lines on the Earth are not great circles, except for the equator, right? So why do we call those the parallels? Because they don't touch, right? But they're not actually straight lines, they're curved lines. So if you were to build a highway along the top of Wyoming, it would curve. It's not straight. If you were to stand and look at it, it would curve to the left or the right, depending on which side you're standing on. Okay. Why do you care? Because on the Earth, there are no such things as parallel lines. They simply don't exist. So what I mean is, if Becca's standing here, and somebody else, it couldn't possibly be a friend, her enemy is standing next to her. I didn't even get a smile out of you. Whatever. And Becca's dad throws her out of the house and says, both of you walk north. So Becca goes in a straight line, and her friend goes in a straight line, and what do you notice? They intersect. No matter how you draw two great circles, they're going to intersect. Because on a flat plane, if you're standing on a piece of paper and you're traveling in that perpendicular distance, right angles, if you're fingertip to fingertip, you're going to stay the same distance apart. But if you're on a sphere, and you do the same thing, you're going to get closer and closer together. No matter how far apart you are, you will always get closer together until you hit. And then you get further apart, and then back where you started, and closer together. Just set at my desk. And I can prove that to you. Here's this basketball. Okay? If I were to draw a line across there, I would have a right angle and a right angle, and you notice that those two lines get closer together. So on a sphere, there's no such thing as parallel. Okay? So Euclid said that if you have a line and a given point, there is exactly one parallel line. As soon as he said that, he eliminated all of this mathematics. Everything he did, all the way from proof 1 to proof 27, worked on all surfaces. He talked about triangles and some side angle side things. Anyways, congruent triangles, similar triangles. He did lots of geometry. As soon as he threw in the fifth postulate, these kids aren't allowed to go to the building. Okay? Which means the Pythagorean theorem does not work on a sphere. The whole a squared plus b squared equals c squared does not work on the Earth. Now here's the great lie that we've been telling you all along. You have been doing planar geometry. Geometry on a plane. And because Euclid came up with the fifth postulate, we actually call it Euclidean geometry. Have you ever heard that term? Euclidean geometry means perfectly flat. So you guys understand Euclidean geometry. The trouble is, there is no such thing as a flat surface. Name me one flat surface in space. Can you think of any? There are none. Okay? Geometry on the Earth is different from geometry on the plane. So why do we study planar geometry? What's that? Well, is it bad that we've been lying to you? Hey, I've never said don't lie. I'm probably lying now. So, here's the thing. The Earth is quite large, and on a very small scale, planar geometry works well enough. If you're building a freeway across a country, like the United States, that would be an issue. But we tend to dodge things like mountains and lakes and stuff like that, so it works itself out in the end. But if you were to actually build a border fence between us and Canada, you would have to curve that fence. That's one application where it would work. So on a small scale, it's close enough that we don't care. If I build my house, it doesn't really matter. One thing, have you ever looked at a land share map? So we break land into 40-acre squares. Well, there's no such thing as a square on a sphere. You either have 4 right angles, and then 2 sides that are equal and 2 sides that are not, or you have 4 equal sides and no right angles. You can't have both because of the way it works. So geometry on a sphere is actually quite different. What is the angle sum of a triangle? 180 degrees. So triangles have 180 degrees. Okay? That is a product of Euclid's fifth postulate. So by saying there's exactly one parallel line, you have guaranteed that all triangles have a 180 degree sum. And I can prove it to you. Here is, if I can find it, a triangle right there. Maybe I should use a different color. Right? What is this angle right here? 90. What is that angle right there? And what is that angle right there? So that is a triangle with 270 degrees in its angle sum. Now, oddly enough, the other side of the is also a triangle, right? It kind of has an inside triangle and an outside triangle. So this angle sum is 270 plus 270 plus 270. So that's much bigger. And in fact, on a sphere, triangles are bigger than 180 every time. The smaller, you can make a really small triangle that's really close to 180, but you can never make it exactly 180. The bigger the triangle, the more it is. No, I'm proving to you that that this parallel postulate is important. So by accepting the parallel postulate, we learned this rule, but that rule doesn't always apply. It doesn't apply on a sphere. Well, let's go back to Euclid's idea, where he said that there's one. So on a sphere, there's actually none, right? And then on a flat surface, there's one. But what if, instead of closer together, the lines actually got further apart? Is that possible? Well, if it is possible, then couldn't I make another set that was a little different? So now I have two lines that are parallel to the given line. Well, if there's two, there must be a third, the one between them, and a fourth, and a fifth, and a sixth, and a seventh. That was cool. So this would actually be an infinite number of lines. So that picture would look like this. Right angle, right angle. So if we were to walk fingertip to fingertip and we go in the same direction, we're actually going to get further and further apart. Let me show you what that would look like. Well, let me show you. So here's a flat piece of paper. If I wanted to turn this into a globe, then I'd cut a slit in it, and I would fold it over a little bit and tape it, and then fold it over a little bit more and tape it and fold it over a little bit more. And if I did that enough times, it would curve. And if I cut a bunch of slits in it going around in a circle, I could make a sphere. Everybody agree? What if I were to take that same idea and spread it apart and put paper in the gap? So the further away you got from the center, the more and more space you had. Here's what it would look like. Flat near the center and wrinkled to the edges. Okay? Now, just like every sphere has a radius, so if this was round, it has a specific radius. This has a bigger radius. A bigger radius means less curvature. There's less curve on the surface. This has a bigger radius. Well, this one has a pretty big radius, and this one has a smaller radius, so it's more curved. And you can see two lines at right angles, and toward the edges, they're really far apart. No. If you're watching each other, you will be. Okay? But if you're like watching a compass or a direction, then your direction will lead you down one path, and their same direction will lead you down a path that deviates. Okay? Here's one that's kind of cool. Look how wrinkled that is. I think I calculated it once. There's something like 12 times more circumference in this than there would be in the equivalent circle by the time you reach the edge. There's 12 times as much yarn on this last row as there should be if it was just a regular circle. So if you did the radius 2 pi r and then compared it to the actual circumference, it's way different. And then these are still flat. You can kind of see on this one. It's just a bunch of spirals put together, and they get so wrinkled. This one was so wrinkled we couldn't fit another stitch. It was so tight we couldn't get another stitch. But again, this is still flat. It's still two-dimensional. So this is called the hyperbolic plane. Hyperbolic plane. And the triangle sum is less than 180. And there's another really crazy thing that happens. You can actually have a parallel line that gets closer and closer and never touches. So they always get closer and closer and closer, but they never actually hit each other. And they're parallel because they go to infinity and never touch. No, you just take the distance and cut it in half. So 1 mile, half a mile, fourth of a mile, eighth of a mile. Yeah, once you get down so close, we stop caring. But the cool thing is, let's say I had one of those. What is the degree measure of that angle? Well, up here it might be 21. What is it here? 6. Then what is it here? And where are we headed? This is actually a 0-degree angle, which only happens in a hyperbolic situation. Well, if I followed this down, and I had another one and another one, what is the angle sum of that triangle? 0 degrees. That's a little bit crazy. And all of the hyperbolic stuff gets thrown out as soon as you start using the word parallel or triangle angle sum. There are other things that are equivalent to this. So my question is, which is the shape of space? Well, it might be important. What if you send 2 spacecrafts on a parallel track out towards whatever you're going for? If space is spherical, those 2 ships are going to crash. It's hard for you guys to realize, but you could actually have spherical 3 dimensions. You could. And what would happen is, as you get towards the edge of space, it would pinch down to the same point. Okay? So imagine a square grid with vertical, horizontal, and depth bars. Okay? If it's perfect right angles, that would be Euclidean space. If it's hyperbolic, then those cubes get bigger and bigger as you spread out. If it's spherical, the further you go, you'd have to find the center of space, which I don't know where it is. They get smaller and smaller. So the question is, if I were to put 2 lasers on this little contraption, so I have these 2 lasers, and those lasers are parallel, and I shine the lights, are they going to touch eventually? Are they going to get further apart? Or are they going to stay the same distance? It depends on the shape of space. So how do you tell what the shape of space is? Well, you could. You could shine the lasers, and then you outrun the lasers, and then measure their distance. Yeah, so that's not a possibility. Einstein proved you can't go faster than the speed of light. Hold on, don't put your stuff away. We're not done. So, you could. Okay, that would work. Here's another thing that would work. All we have to do is measure a triangle. Now, the catch is, whatever the radius of space is, then you would have to have a triangle that was in proportion very large. And the trouble is, things in space don't tend to hold still very well. And it even takes like almost 2 seconds to shine a light from Earth to the moon. And even that, so measuring triangles is sort of a problem. Yes, it takes 8 minutes for the sun's light to reach Earth. Right, if the sun shut off 8 minutes later, then it would go dark. So probably not. It'd go totally dark. No, it'd be dark. It'd be dark. It'd be light. It would be light on Earth. You see the sun, light goes off, no sun. Same time. Okay, hold on. Listen to this. So, here, instead of trying to figure out exactly what it is, let's talk about what it's not. How many different spheres are there? How many different sizes of spheres are there? An infinite number. Okay? Everywhere from nothing up to an infinitely large sphere. How many hyperbolic radii are there? Infinite. Okay? How many flat surfaces are there? One. So, if we believe in probability, what is the chance that space is Euclidean? 1 out of 2 times infinity plus 1, right? It's 1 out of this plus this plus this. So if we believe in the laws of probability, 1 divided by infinity is actually 0. There is a 0% chance that those lasers are going to stay the same distance apart. So you hear about space expanding. It very well might be hyperbolic. It might be bigger on the edges than it is in the center. We do have like, you can do math on a donut. I doubt space is shaped like a donut. But these are the three basic ideas. A sphere, a donut is really just a fancy sphere. So really, you're looking at one of these three possibilities. Yes. If space was circular, and you sent two things into space, eventually they're going to hit each other. Near the end of space, you would have to stop. But near the end, you would hit each other. We don't know. We've never been there. We don't know. We don't believe that space is infinite because we can't prove it. Every time we build a bigger telescope, space tends to get bigger because we can see things further away. So your assignment tonight, flip this page over. You have 13 definitions to write. So you have to be careful when you write these definitions. I don't want you to look them up. I just want you to write down what you think the definition is. And then I'm going to shred your knowledge.